Continuing through these Unit 1 practice problems, we are now on question 22. Consider the function model s of t equals negative 0.57 times t minus 12.2 squared plus 93.1 with application domain 0 to 10. So we've got some function with a limited domain, a restricted domain. And then we have a bunch of questions about it. Now, later on in the course, we'll learn more about this type of function so that we can quickly identify things like, well, all of these things without even graphing it. But for now, we don't really know much about this, so we're going to graph it to determine what type of function we're looking at. So that just means we got to type everything in. I'm going to clear everything. You know what? I take that back. I'm not going to clear everything. I'm going to clear this as needed. I'll just clear those two. And let's enter our function. So that's negative 0.57 x minus 12.2 squared plus 93.1. And then I know already that I'm going to go from 0 to 10. 0 to 10 is my x min and x max. So that's 0, 10, and then I'll do zoom fit. Okay, so we have a decent picture of this region. And what are we looking at? Is it concave up, concave down, change in concavity, etc.? This is an increasing function, but it's increasing at a decreasing rate, i.e. it is concave down. This is concave down. Then we can, oh, and I skipped the first question. Didn't I? Find the function's application range. Sorry. Let's go back to that. So how do I find the application range? Using interval notation. Since this function is strictly increasing, if I know the value of the function here and I know the value of the function over here, then I'll know the range for this application domain. So basically, I just need to evaluate the function at 0 and then evaluate it again at 10. So I will exit. There is another way to do this using a function called calc value, but I've avoided that so far. So I'll just do this using vars yvars. So y1 of 0 is 8.2612. So that's going to be the beginning of my range. And the end of my range will be vars yvars function y1 of 10. And that's 90.3412. And that's my range. Okay, now we can go to part C. So complete the following table. We haven't done quite as much of this in this unit, but I'll go ahead and answer this question using the delta list function. So if you haven't used this very much, this is a method of calculating multiple average rates of change. And this is all going to be done in the calculator. If we didn't use the delta list method, this would just be somewhat tedious. So let's go to, and I do need to clear my list, so let's clear the lists. And L1 will be 0, 2, 4, 6, 8, 10. L2, what is L2? L2 is the function evaluated at each of these. So what we're actually going to end up typing in here is y1 of L1. And what that will do is evaluate it will use the function y1 and evaluate it at each of these inputs. So this is sort of the smart way to do this multiple times. So I haven't gotten to the average rate of change yet. So move your cursor to the header. Notice that I'm moving it up here. Okay. And then we go to vars, yvars, function y1, parentheses, second, list1, hit enter. And now I've evaluated the function through this first list. Okay, so now we're ready to move on to column L3. And let me go back here. What I'm going to end up putting right here is this. It's going to be delta list L2 divided by delta list L1. Okay, and that's going to calculate multiple average rates of change. So again, notice that I moved my cursor to the header of L3. Go to second list, ops. Number 7 is delta list. L2, that's the numerator. Then we hit the division sign. Do second, stat again for list, ops again, number 7. And second, number 1 is L1. Close your parentheses and hit enter. And there's our values. So these values that you see right here are what you need to transcribe into the table here. So let me bring those back up. So 12.768, 10.488, 8.2. So, and notice that you don't have anything in this last entry. That's intended. So you see it's blanked out here as well. Because we'll always have one fewer average rate of rates of change than we will intervals. Or sorry, numbers here. Because we have one arc for this interval, one arc for this interval, one arc for this interval, and one arc for this interval. Okay, and there's your answers. Okay, all right, let's move on to question 23. Each month, a water utility assesses each household in its service area a flat fee of $5.95, along with a fee for the water they use on the following basis. The usage fee is 0.9 cents for each gallon used through the 5,000th gallon, and from then on, the per gallon fee is 1.4 cents. Write a formula for the customer's monthly total water bill in dollars as a function of their water usage U in gallons. Okay, so I'm going to draw this. I'm sensing a piecewise function coming along, and it always helps me to have a picture. So looking at this, it says write a formula for the monthly total water bill as a function of water usage. So this is going to be water usage, U, in gallons. And this is going to be water bill in dollars. So we start off with a flat fee of $5.95. Then when we get to the 5,000th gallon, so we're increasing linearly at a rate of 0.9 cents. So I don't exactly know what to put here, but I do know that I can say this. I can say that the slope is 0.9 cents. Actually, I need to be careful about this because I said the slope is 0.9 cents, but the unit here is in dollars per gallon. So we do need to be careful and make sure that all our units are fine, okay? So let's actually think about what the slope is in the correct unit. So for this first piece anyway. So if it's 0.9 cents, my unit conversion to dollars is 100 cents is $1. So basically we just need to divide this by 100, which is going to give us a smaller number. And that's 0.009. And so actually, I should go up here and fix that. My slope is $0.009. That's supposed to say dollars. Let me make this a bit larger. Dollars per gallon. Okay, so that's the slope of my first piece. And then I go up to 5,000 gallons. And when we hit the 5,000 gallon mark, we now are charged more per gallon, which is 1.4 cents per gallon. So we have a new slope. So we've got to figure that one out as well. And so that's going to be, notice that I just moved my decimal place over 2, so that's what this is going to be. It's going to be $0.014 per gallon. And that's going to be my next slope. So it's going to look something, a slightly steeper line. Okay, now none of this is the actual equation of the line, but it does make it easier, I hope, to compute our linear equation. So let's go down here and actually write this. This is going to be a piecewise equation, and remember our unit is going to be W of U, right? So the first piece is going to be valid for U between 0 and 5,000, and the next piece is going to be valid for U greater than 5,000. The first piece is going to have slope 0.009, and for this piece I can use mx plus b, because if you go back to your graph, oops, I'm sorry, no, I can't use mx. Yes, okay, yes, we can use mx plus b because we know b is 5.95. So mx plus b, so that's 0.009 u plus 5.95. That's piece 1. Now for piece 2, I'm going to have to use this because I don't know the y-intercept for piece 2. Now I do know the slope. The slope is 0.014. And for my x1, y1, what's that going to be? Well, I'd like to use this point right here. I don't actually know the coordinates of it though, but I can figure it out because its input is 5,000, and therefore the output, we can just plug it into this model that we just found. So that would be 0.009 times 5,000 plus 5.95. And that's 50.95. So, and that'll be my x1, y1 for piece 2. So this is going to be u minus 5,000 plus 51.95. Oops, that's 50.95, not 51. My bad. All right, and there is our piecewise function. This stuff up here is just to guide you in which model you used. You actually wouldn't keep that in the answer. We would erase that. So that's your answer.